In this lab, we will talk about Taylor approximation. If you have covered linear approximation in class, then this is just a generalization of that, and so some parts will look familiar. We start with adding our usual libraries. We will also add a few extra variables to use with SymPy. The main idea behind Taylor approximation is to approximate a function with a polynomial of some fixed degree. We need to know where we are approximating, and in this lab we will always approximate near zero for simplicity. And the next, we want to find a polynomial whose value and values of its first few derivatives equal to the value of a function and to the values of its first few derivatives. In this file, we will discuss a function f of x equals 2 over x plus 1. And so our first approximation will be with the polynomial of degree 0. So in other words, a constant function. All we really need is that the value of this constant function equal to the value of our function at 0. Since f of 0 is equal to 2, we will define our constant function t0 of x to be just 2. And this is our first approximation. And now let's plot both our function and its approximation. So we define our function f of x. We define our constant approximation t0 is 2. And we will plot. We will plot our function in blue color. We will plot our approximation in red. Notice I am using a horizontal line command to plot constant function. It's actually easier to do that way instead of plotting it as a regular function. My x values will go from negative 0.99 until 2. I'm trying to avoid negative 1 here so that I don't have a division by 0, since my function is undefined at negative 1. And this is the graph. As we can see, in blue we have our f of x, and in red we have our constant approximation near 0. Next, we will try to approximate the same function using a linear polynomial. So we want to find a linear function that we will call t1 of x that approximates our function at 0. We will make it equal to t0 of x plus some linear term ax. Notice already t1 at 0 equals to f of 0. So what we want to achieve now is that it's the first derivative of t1 of 0 also equals to f prime of 0. So we will find derivative of f of x, we will find derivative of t1 of x, we will make them equal, and it will allow us to find this value a. So let's try to do this. So here's the derivative of f of x evaluated at 0. It's minus 2. Next, we'll create our t1, which is t0 plus ax, and we'll find the derivative of this linear function. It's a, and therefore we want our a equal to negative 2. So we will redefine t1. So now t1 is t0 plus negative 2 times x. So this is 2 minus 2x. And we will plot both of them. As you can see, we have again our f of x, and this is our linear function 2 minus 2x. In essence, this is just a tangent line at 0. Next, we will try to approximate our function using a quadratic polynomial. The idea is very similar. We will create a quadratic function that we will call t2 of x. It equals to t1 of x, which is a linear function, plus a quadratic term bx squared. Notice already the value of both t2 and f at 0 are the same, and the value of their derivatives at 0 are the same. So to find b, we need to make their second derivatives equal at 0. So we will find the second derivative of f, the second derivative of t2 of x. We will make them equal, and this will allow us to find b. So here's the second derivative of f evaluated at 0. It's 4. Now we create t2, which is t1 plus b times x squared, and we'll find the second derivative of that. It equals to 2b. So 2b equals to 4, and therefore b is 2. So again, we redefine our t2 to be t1 plus 2 times x squared. This gives us this quadratic function, 2x squared minus 2x plus 2. And now we plot. We will plot both our function and our quadratic approximation. And there we have it. Notice the red, which is a quadratic approximation, is much closer to our function near 0 than the linear approximation we had in the previous example. And we will do this 2 more times. So we will create a cubic approximation. So this is the third derivative of f, which is negative 12. We create our cubic approximation, which will be the t2 plus c times x cubed. We find a third derivative of that. That's 6c. So then 6c is equal to negative 12. Therefore, c is negative 2. We redefine our t3. You can see now it's a cubic polynomial, and we will plot both of them. So here's the red is our cubic approximation. We can do it one more time. Let's do this for a fourth degree polynomial. So we find a fourth derivative of f, which is 48. We create our fourth degree polynomial, which is t3 plus d times x to the 4. We find fourth derivative of that. That's 24d. So we solve for d. We get that d is 2. And we have our fourth degree approximation. And this approximation is even better. And you can go as high as you want this way. The higher the degree, the better will be your approximation. Now, you can also approximate your function at some other points besides 0. This will not be needed for this lab. You will not be asked to do this. But if you want to play around with this, the only thing you need to change is how you define your t0, t1, t2, and so on. So t0 would be just f of p. T1 of x will be t0 of x plus a times x minus p. That's the new part here. The t2 of x will be t1 of x plus b times x minus p squared, and so on. So notice instead of just having x here to some power, you will have x minus p to some power. And that's it. One of the problems in the lab will be about differentials and linear approximation. If you haven't covered this in class, let me introduce some small concepts so you can start the problem. Suppose you have a function f of x and some point x. We will define delta x to be a small change in x. Delta x in essence is just a very, very small number. Then we can define delta y to be a change in the f values. So it's f of x plus delta x minus f of x. You should try to compare this to the average rate of change formula, specifically delta y divided by delta x. Then we'll define differentials. Differential dx is just defined to be equal to delta x, so that's quite simple. However, differential dy is equal to f prime of x times dx. Now this is enough to start the problem, and the rest of it will be explained by the problem itself. But just to give you maybe a quick way of understanding what dy actually is, it's in essence an error of linear approximation. In other words, it's how much the linear approximation at some point x plus delta x differs from the actual value of the function. And now let me say a few things about the actual lab problems. The Lab 5 will consist of 4 problems. The first problem will deal with differentials and linear approximation. The second and third problem will deal with Taylor approximation, which is what this whole example file was about. Finally, the fourth problem will deal with optimization problems. Here you need to recall how to do polynomial models and how to take derivatives of polynomials.